All right, so in this chapter, we're going to actually take on a couple of different topics that are kind of related to each other. What we're going to be looking at is molecular shapes, and then we're going to be looking at also, and the properties that they affect, and then we'll also be looking at two other bonding theories, which are really separate in some ways from Lewis theory, and allow us to incorporate quantum mechanics and some of the results of quantum mechanics in understanding how atoms bond to form molecules or ions. So let's get started with VSEPR theory. And VSEPR theory builds off of Lewis theory. So Lewis theory tells us how atoms are connected in a molecule, and then what VSEPR theory does is tell us how the groups that are on an atom will space apart from each other and obtain three-dimensional or two-dimensional geometries. So valence shell electron pair repulsion, or VSEPR theory, right, is dependent on this idea of electron groups, which we kind of introduced a little bit in the last chapter and in the Lewis structures worksheet. An electron group is any grouping of electrons that are pointed in one direction or on one side of the atom. And so these include lone pairs, single bonds, double bonds, and triple bonds. And because these are all electron groups, what they do is they repel each other, and their goal in life is to get as far away from the other groups as possible. And by maximizing the distance between the groups, they minimize the instability or minimize the molecule's energy. So the whole idea of VSEPR theory is maximizing electron group distances to get lower energy. So VSEPR theory is again based on the ideas of Coulomb's law. And so imagine that you have a central atom and it's bonded to atoms, right, other atoms. And remember, there are attractive forces going this way. And that's what we call the chemical bond. So you have these electrons. They'll be in between the atoms because they're attracted to the atoms, right? That they're helping to bond to the central atom. But at the same time, because these have like charges, they tend to spread as far apart as possible from each other. So for instance, in this example, because the groups want to space as far apart as possible from each other, they essentially form a triangle. And that triangle, if you looked at it, would all be in a single plane. So we would call this arrangement a trigonal planar arrangement. And there'll be other names like this, but the essence is move as far apart as possible to get the lowest possible repulsive energy between the groups. So what are electron groups, right? So I defined them earlier, I said what they are, but it always helps to see an example. So when we're doing the shape, we're really talking about electron groups on, in this case it's nitrogen, but this is the central atom, okay? So, like I said, electron groups can be a lone pair, single bond, double bond, and triple bond. So if we just look at the nitrogen, all we have to do to identify the number of electron groups is just identify there's a double bond, there's a single bond, and there's a lone pair. So just doing that, there's 3 groups on the central atom. Now, if I were to draw that the way it's supposed to look then, without actually filling all the lone pairs in on the oxygen, you notice I ignored those when I was trying to determine the number of groups on the nitrogen. The nitrogen would be in the middle, the lone pair would be, let's say, on top, and then down around here you would have the oxygens, okay? Now, let's go back to the diagram earlier. This is kind of flipped over. But if you think about what the angle is between this atom and this atom, well, it's 360 degrees, and it's split up 3 different ways. So 360 divided by 3 is 120 degrees. So what we have in nitrite ion is a bond angle that's here of about 120 degrees, right? And the electron geometry is trigonal planar. Now, this molecule has resonance. And it says here that resonance does not affect the electron group geometry. So what that means is if I had drawn the nitrite ion like this with the double bond on the right, I would have still had a single bond on the left and a lone pair at the top without filling in all the electrons on the oxygens. And this is still 3 electron groups around a central atom. So just because an atom has resonance doesn't mean it changes its electron geometry as it goes between its resonance forms. So we have a thing called the electron geometry, and I took the liberty to redraw the nitrite ion, its general shape anyways, on this slide. And again, 3 electron groups, trigonal planar electron geometry. Now, this is not, when we refer to the shape of a molecule though, so not the electron geometry, but we call the molecular geometry, right? Electron geometries describe group arrangements that include the lone pairs, and then the molecular geometry just tells us what the atoms are arranged like and ignores the lone pairs. So you notice how this molecule has this sort of shape like this, all right? Has a 120 degree bond angle roughly. We would refer to this as bent. Again, there's going to be a whole series of these names. And again, resonance doesn't change the molecular geometry or the electron geometry. But the number of lone pairs affects what the molecule looks like in our terms of molecular geometry. Okay, so electron geometry, electron group arrangements includes lone pairs. Molecular geometries, we just ignore the lone pairs and say, what's the shape of the molecule look like? So now what I want to do is to take you through some of the different electron and molecular geometries that are common, and especially ones that we'll see in this chapter. Okay, so if I have 2 electron groups, right, the electron groups will always be opposite of each other, and the molecule will always be linear. Now, beryllium chloride is an exception to the octet rule, but still, there's just 2 electron groups. There's an atom here and an atom here, single bonded on both sides, and it produces a linear geometry. The bond angle will be 180 degrees. Carbon dioxide also has 2 electron groups, even though one of them's even though they're double bonds, right? There's still only 2 electron groups. Here's one here, one here. So what beryllium chloride and carbon dioxide share in common is they both possess a linear geometry, electron group geometry, and molecular geometry, and the bond angle is 180 degrees. When I do 3 electron groups, then what I end up with is what's called the trigonal planar electron geometry. Right? Trigonal planar, again, the way we get the bond angles, we look at the number of ways 360 can be divided, so we get 120 degrees. I should have pointed out back here, you take 360 and you divide it in half, and then you get 180 degrees. So sulfur dioxide, when you draw its Lewis structure, has a bond angle of 119.5. It has 3 electron groups. The double bonded oxygens, right? Those double bonds count as a group, and then there's the lone pair. So again, this molecule is flat. That is, all atoms lie and the lone pair here all lie in the same plane, okay? And the bond angles is about 120 degrees. Now, the 4th electron group actually forces us to go to 3 dimensions in our shape. So if you're trying to get a 4th group in, you can get the 4th group to be at 109.5 degrees of the other groups if you put it on top. So you might have seen this in a couple of different places. So if you go to the grocery store and you've seen how the grocer stacks up fruits and vegetables, especially if they're round, right? If they're round, you'll see this kind of structure as one of the basic units of the stacking of the fruit. And this is known as a tetrahedral geometry. So in the tetrahedral geometry, the atoms that are connected to the central atom form a tetrahedron. So what's not shown in this diagram here, when they call it a tetrahedron, they're not showing the atom that's in the middle, which is the central atom of the molecule. Now, this has a 109.5 degree bond angle, and there are several different kinds of molecules that would make this. So for example, if we drew methane, methane's Lewis structure looks like this, and we have 4 electron groups. Now I always circle the atom along with the bond, but really we're just focusing on the bond. This is 4 electron groups. Now, what you have to always be careful with, and this is one of the things that's really tricky about doing these things when you see them on paper, you've gotten used to drawing them like this, but in reality their shape is like this. So you have 3 hydrogens at the bottom, for example. There's a hydrogen here, here, and then there's one back here that you can barely see. And then you also have a hydrogen sphere stacked on top, and in the middle of this whole mess, down in here, right, that's where the carbon is at, and I can't really circle with yellow too good, but maybe you can see that okay. So what other kinds of molecules, right, take this kind of geometry? And one of the ones that I think most everyone recognizes is H2O. So when you draw the Lewis structure for water, you'll get a Lewis structure that looks like this. And everybody's tempted to look at this and say, oh, what's the bond angle between the hydrogens? So they would say the hydrogen-oxygen-hydrogen bond angle. And lots of people are tempted to say that this is 90 degrees, but you have to remember that this molecule is arranged 3-dimensionally, just like this balloon model is. So if I were referring to this balloon model, and referring to it as water, right, I have 2 lone pairs. So that might be this group here, and maybe this group back here. And then out in the front, I have hydrogens like this. And the oxygen is in the middle, like this. And so I have a bond going from this hydrogen to this hydrogen, like that, with the oxygen being this circle in the middle. And even though on paper it looks like 90 degrees, it's actually 109.5 degrees, roughly 109. And I'll talk about the details of that. It turns out the bond angle is slightly smaller because of the lone pairs, but in principle it should be around 109 degrees or smaller, because it's actually coming from this tetrahedral geometry with 4 electron groups. I was going to say, there's a little for fun slide in here. It's only fun if you like geometry. But it goes about showing how the bond angle can be calculated as 109.5. And I'm going to skip that in the lecture, but I just kind of put it in there for people who are curious how we know it's 109.5. All right. So let's try this problem. It says, what is the geometry, and we're looking for electron geometry of the HCN molecule. So what does this boil down to, right? You have one group here on this carbon, and you have another group here on the carbon. Again, we always focus on the central atom. So we have a total of 2 groups, which means its electron geometry would be linear. So often in high school chemistry and in introductory chemistry, I know for sure at Reedley College in Fresno City and other introductory to chemistry courses that I've taught. We usually stop at 4 electron groups, but there are a number of molecules which have more than 4 electron groups. In fact, you can have 5, 6, and then in this class we don't cover 7, but there's even 7 and higher numbers of electron groups. And really what limits us in situations like this to 4 electron groups is we're thinking about s and p orbitals and being able to bond to 4 different groups through the combination of the s and the p orbitals. Once you get to energy levels 3 and higher, though, and we've seen this in our drawings of the Lewis structures and things that we've called expanded octets, that you can have more than 4 groups on the central atom. So when we get additional groups on the central atom, this changes the number of possibilities for electron and molecular geometries that we get. So 5 electron groups, right, becomes something known as a trigonal bipyramid or a trigonal bipyramidal geometry. And in essence, the way the trigonal bipyramidal geometry works is for this molecule example PCl5, we have 5 groups on the central atom with no lone pairs on the central atom. The chlorines around the equatorial region, so the equator, right, like on the Earth has an equator that goes around the sides, is actually in the trigonal planar geometry. But it has a group at the top and the bottom in the middle to give us this trigonal bipyramid. So a trigonal pyramid, if you were to cover up the chlorine down here, a trigonal pyramid would be a pyramid that has 3 corners at its base. When you look at the pyramids, for example, in Egypt, those are square pyramids because the base is a square. That is, the part that sits in the sand has a square shape to it, and then the pyramid is the peak at the top, right? Goes up to the peak in the center. So we have 2 groups in addition to the phosphorus on the central atom, right, on the axis, and on the equatorial positions we have 3 groups in a trigonal planar geometry. So when we look at the bond angles in a trigonal bipyramid, the groups that are going vertical are at 90 degrees to the ones in the equatorial position, and the equatorial atoms are 120 degrees, right, the trigonal planar part, 120 degrees apart from each other. If you take balloons and you want to try this, it's not too hard to do actually. What you do is you go ahead and you make 5 balloons and you tie them together in the middle, and they'll naturally take this shape. And the reason they take this shape is because the balloon's volume acts like repulsive forces for Coulomb's law, and these will spread out as evenly as they can around the central axis while allowing the top and bottom ones to poke out. That's the lowest energy configuration for 5 balloons tied together in the middle. The trigonal bipyramidal shape could also be shown like this, and I think this part, this part here, right, shows us sort of the trigonal pyramid part of it the best. In this case, the pyramid is pointing down, and this is the side that's facing towards us. And then we've got a side that's to the left, and then there's another side in the back that you can't see that's connected by these corners here. Okay. Now we can add one more. And in fact, you could add 2 more, but as far as we go in this class, you can add 1 more. And now you have 6 groups on the central atom. So sulfur hexafluoride has 6 electron groups, no lone pairs. This is known as an octahedral geometry. And the reason they call it an octahedral geometry is because it makes an 8-sided object. Okay, so if you're looking at balloons, there's one face right here, then there's another one here, and there's another one here, so that's 3 faces, and then there's one in the back, so that's 4. But that's only describing the faces that are at the top. And then on the bottom side you have 4 more. So an octahedron implies it's an 8-sided object. So this creates the 8-sided octahedron that you're seeing here. Although it's not quite rotated the right way, right? You can see like this corner should be this way and this corner should be up here somewhere, so it matches the balloons here. But that's the octahedral geometry. So I describe trigonal planar and bent. And I think what we need to do now is, and as trigonal planar as the electron geometry way back here, right, trigonal planar, and then I talked about the molecular geometry being bent. What I want to do now is look at those same kind of relationships for the tetrahedron, the trigonal bipyramid, and the octahedron. So when you have 4 electron groups, you have a tetrahedral electron group arrangement, but there's 3 different molecular geometries associated. One is called the tetrahedron. So tetrahedron, right, tetrahedral electron geometry and tetrahedral molecular geometry is one in which the central atom has 4 groups and no lone pairs. For some reason they don't have drawn on here. There should be hydrogens at each one of these points here. I think is what they meant to do, but I'm not sure. So that would be like ammonium ion. Now if I had ammonia like this, right, then one of these groups is a lone pair, and now it just makes a trigonal pyramid. Remember we talked about a trigonal bipyramid? Well, that's with a trigonal pyramid at the top and the trigonal pyramid at the bottom. But in this case, I have a single peak in the middle and then a triangular base at the bottom. Now, the bond angle for this ideally would be 109.5, but it turns out that lone pairs, because they're not directed towards a positive charge, actually spread out and take up a little bit more space. Since lone pairs take up more space, then what happens is the angle that's left for the atoms that are remaining becomes smaller. So this angle from the lone pair to the hydrogen gets bigger, and as a consequence, the angle that's left between the hydrogens gets smaller. Now, water was also one of the tetrahedral electron geometries, but it has 2 lone pairs, and when you look at its structure, right, the 2 lone pairs occupy more space, so the angle that's left between the hydrogens is even smaller than that of ammonia, which is 104.5. Now, I don't particularly want you to know specifically the smaller angles, but for sure you need to know this angle. It wouldn't hurt you to know water's 104.5 because it just comes up so often. But what you do need to know is that the electron lone pairs take up more space and leave less space, so you expect the bond angles to get smaller as the number of lone pairs on the central atom increases. So and this is actually just a cleaned up version of 4 molecules, methane, which we showed earlier, ammonia, and water, and how the bond angle goes from 109.5 to 104.5, and they're not showing the lone pair. So this is what we mean by molecular geometry. But the molecular geometry is set up by the electron geometry, so the bond angles would all be closely related to each other. Another sort of terminology thing that you have to be aware of is that they often say that the lone pair repulsion is stronger than the lone pair bonding pair, and is that stronger than bonding pair interactions. So what they're trying to say when they write these kinds of things out in your book is that the interactions between this pair of electrons and this pair of electrons, that's a bonding pair interaction, is the weakest repulsion. But here on the oxygen, you have a lone pair up here and a lone pair back here. This is a lone pair interaction. That's the strongest kind of repulsive interaction. That gives you the smallest angle that is left for the atoms in the molecule. So when we're looking at 5 electron groups, we have a trigonal bipyramidal electron geometry. And then turns out there's 4 molecular geometries that come out of this, one of which we call trigonal bipyramid, just like we do for the electron geometries. And that's the molecule like PCl5, where there are atoms at every one of the 5 positions. And then when you have one lone pair, as in SF4 here, right, we have 1 equatorial, and then BrF3, we have 2 equatorial, and then linear, we have 3 equatorial pairs of electrons. This shape is known as seesaw. It's a little bit hard to see it, but it's like an old-fashioned teeter-totter that you'd see in a playground. It has that kind of shape where, the kids would sit here. I don't know, something like that. And they would hold on to handles, right? And you go up and down on either side. That's what this kind of shape looks like if you lay it on its side, so that's why it's called seesaw. T-shape literally looks like a T, but it's turned sideways. So the T is actually going this way. And linear is just linear. It's a straight line. Now, if you're looking at this structure for, let's say, seesaw or T-shape, you realize that all the electrons always come off the equatorial position. And that's probably the most important thing to remember. The reasoning behind it is pretty straightforward. You have 2 options of arrangements where you could replace one of the axial groups with a lone pair, that's this one, or one of the equatorial groups with the lone pair, and that would be this one here. So why does it choose to put it in the equatorial position? And the answer is actually pretty simple. When you have a lone pair, right, it interacts more strongly or less favorably, it's more repulsive to a bonding pair. And when you have it in the axial position, it has interactions with 3 bonding pairs. If you put it in the equatorial position, it's further away from these bonds, and there's only two interactions at 90 degrees with bonding pairs. And so this has 3, if we were keeping track, 3, sorry, I'm trying to get my pen to write. 3, there we go, bond pair, lone pair interactions. And here we have 2 bond pair, lone pair interactions. The bond pair, lone pair interaction, one would be, for example, this, and the other one is with this group up here. Here on the left we have 3, and one of the groups, for example, would be, one of the interactions would be this one, and then it's with all 3 here on the equatorial position. So as it turns out, because there are fewer unfavorable interactions here, this is the preferred shape for one lone pair in the trigonal bipyramidal electron geometry. So there's only one more electron geometry to go over, and that's with 6 groups or 6 atoms on a central atom. And this is the octahedral electron geometry. And when you have no lone pairs, this is also known as the octahedral molecular geometry, or shape. Now, if you remove one lone pair, unlike the trigonal bipyramidal structure, it doesn't really matter which one you take it off of, because you'll always be left with essentially the same structure, just rotated. So, for example, if I put the lone pair here and the fluorine down here, it would just be the same structure rotated by 90 degrees. So, this shape is known as a square pyramid because it's a pyramid shape, just like the trigonal pyramid, but it's square at the bottom. And so this looks like the pyramids that you would see when you go to Egypt, for example. Now, when you take this second atom off and you replace it, and you make what's called a square planar arrangement, And the lone pairs are on opposite sides of each other, so they don't have to be at 90 degrees, because that's the only other option if you move one of the lone pairs. So if you move this lone pair to here, then you'd have a lone pair interaction, which is very unfavorable. And so the molecule arranges itself so that the lone pairs are top and bottom with respect to the central atom. So this is a replica of the table that you'll find in your textbook. This is a summary of how you categorize electron groups and molecular geometries and electron geometry. So if you have two lone groups, two of those are bonding groups and no lone pairs. So bonding groups are attached to atoms, okay? Then this structure would be linear. If you have three groups, and three of those are bonding groups with no lone pairs, then it's trigonal planar. But then if you have three electron groups, two bonding, one lone pair, right? That's the category. So this column, these two columns always add to be what this column is on the left. But you have two bonding groups and one lone pair. The electron geometry now is different because you have a lone pair. It's trigonal planar, but the shape we've referred to as bent. Four, right, with no lone pairs would be tetrahedral. This is some of the structures we looked at before. And again, it goes through 4 electron groups and then 5 electron groups. And 6, which for some reason I don't have the slide here. So apparently I got them out of order. So there's 5, right, electron groups and all the various electron geometry, which is all the same for 5. And then molecular geometries in 6. Okay, so you need to be fluent in using this chart. If you plan on going on further in chemistry, for example, Chem 1B or organic chemistry especially, you should become really familiar with at least electron groups 2 through 5. 6 we don't see very often if you take advanced organic chemistry for some reason at some future date, like 3 years down the road. This shows up in a few places. But for the most part, we see trigonal bipyramid occasionally in when we're trying to study how reactions happen, and we see tetrahedral all the time. This is one of the common ones for carbon and all of the atoms that we see in biological molecules. So it's very good to know 1 through 4 for biology. If you're going to take organic chemistry 2 through 4, and then 2 through 5 for organic chem and biochemistry, physiology, pharmacology, all those kinds of things. Those are where you see those. All right, now let's do a practice example. So there's 2 structures here, and your goal is to draw the structure, identify the electron geometry, and identify the molecular geometry. And so what you need to do first is draw the structure. So I'll pause, draw them, and we'll run through it really quickly how I got them along with formal charges. And then we'll go ahead and we'll look at the electron and molecular geometries. Okay, so those are the Lewis structures and some of the quick calculations I did for valence electrons. I actually did these ones separately. For ozone, I just did 3 times 6, so it was 18. There were 4 in the skeleton, so that left me 14 left remaining to distribute. So I had the 14, but then I didn't satisfy the octet on the central atom, so I had to donate a pair into here. For PCl5, PCl4 minus, there were a total of, oh, I forgot to fill all these in, my bad. Total of 34 valence electrons, because there's 5 for the phosphorus, 4 times 7 for each, there's 4 chlorines, they each have 7, and then 1 for the -1 charge. So I ended up with 34 valence electrons. The skeletal electrons, oh, yeah, sorry, let me fix this. Sorry, I started doing the 4 times 2 here, and I sort of stopped for some reason, but this 8 skeletal electrons leaves 26 remaining electrons. I distributed it all the way around the chlorines, and then I had 1 more left, so I stuck it on the phosphorus. Now for formal charges, I calculated those 2. The phosphorus one definitely looks weird, so I went and checked it, and that comes out to be -1. And then for the ozone, the central oxygen is +1, and the oxygen with the 3 lone pairs is -1. Okay, so we want to classify the electron geometries and the molecular geometries. So the first thing you need to do is figure out the number of electron groups. So for the central atom, I have 3 electron groups, and that includes a double, a single, and a lone pair, right? Double bond, single bond, lone pair. And I have 1 lone pair. So if you want to classify this, you may already remember that that shape is bent, but you could also go up to here. I have 3 electron groups and 1 lone pair, 2 bonding and 1 lone pair. So that's going to be trigonoplanar and bent. So often we'll say TP, because there's 2 ways to get the bent geometry, so we often say TP bent. Now, for the PCl4-, I have 5 electron groups on the central atom. So there's 1 as the lone pair, 2, 3, 4, 5. So 5 electron groups. There's 1 lone pair. And if you remember this shape, this is the seesaw shape. And you can go back into the chart and find 5 and 0, and then 5 and 1. It's a trigonal bipyramid seesaw shape. Okay. So just to summarize how you do this process, right? You draw the Lewis structure, you determine the number of electron groups around the central atom, you classify each group as either a bonding pair or a lone pair, and then you count each type. And if it's a multiple bond, right, it still counts, or a lone pair, it's 1 electron group. And then table 11.1 is what we use to determine the shape. So a big summary, sort of big picture summary of VSEPR theory. Bonds and lone pairs make up electron groups around a central atom. And then Coulomb's law predicts that these groups will space apart as far as possible to lower their potential energy. So the electron geometries then establish the angles for the molecular geometries, which only show the bonding pairs. So electron repulsion sets up the angles and the overall shape of a molecule, but when we're talking molecular shape, we ignore the lone pairs. Not that they're not important, but they, in terms of how the bonding looks in a molecule, that part of the shape, we just look at the bonding pairs. Now, bond angles are generally pretty close to ideal. So, for example, 120 for trigonoplanar, or 109.5 for tetrahedral, that kind of thing. But they vary a little bit because the group repulsions vary a little bit. Lone pairs repel lone pairs the strongest because they're not focused on atoms that they're bonded to, so they sort of diffuse out a little bit. And then lone pairs versus bonding pairs, that's a little less repulsion. And then bonding pairs have the smallest repulsion. And it also turns out that triple bonds take up a little bit more space than double bonds, and single bonds take up the least space. And that kind of makes sense because in a double bond or single bond you have 1 pair of electrons, whereas in a triple bond you actually have 6 pairs of electrons. And so that causes some extra repulsion and can cause things to space out a little further.